So one of the main areas where dynamic programming really shines is in optimization problems. Optimization problems meaning finding the maximum or finding the minimum, finding the most ways we could do something, the least ways that we could do something. When you see that kind of optimization problem, you're almost always going to be reaching for dynamic programming. So let's talk about another example. Suppose that we modified this idea of our stairs a little bit. You could still take either one or two steps in order to reach the top of the steps. However, there's a difference. The difference is that on each step, the step that you move towards will have a cost associated with it. So one step may cost you 100, one step may cost you 10, and your goal is to consistently determine what the lowest possible cost is to traverse the steps. So let me just give you an example of this just to make it maybe a bit more clear. I would generally say that we would be given like an array of costs. So you're going to be given something that looks, say, like this. So in this case, the first step would cost you 1, the second step would cost you 100, these three steps all cost 1, this step costs 100, these steps cost 1, this one costs 100, this one costs 1, right? And the idea is that if I were to approach this, well, I would probably end up taking one step to start at 1, then I take 2 steps to end up at 1 again. I would take 2 steps to get to 1, and then from here I would take 2 steps to get to 1. I would take 1 step to get to 1, and then I would take 2 steps to get to 1, giving me a cost of 6 overall, right? So that would be the most efficient way for me to climb these stairs. So do you see that we're really just moving through trying to find the thing that has the lowest cost at each step and taking that option as our result? The way that that looks in code is basically like this. I'm going to call this min cost climbing stairs. We'll take in an array of costs. What we do is we start by getting the length of costs, right? Since we're going to be sort of using this primarily inside of our iterations, right? And we're going to set up our memorization of some sort, right? Our tabulation in this case, since we're going to be using a bottom-up approach. And the idea is that I want to store n possible options, because n is the length of costs in this case. My question is, so what is the initial value? So in order for this to really work, we know that we could take either 1 step or we could take 2 steps. And at the beginning, I need to have the result of basically choosing either to take 1 step or 2 steps. So usually that means that we want to get dp at 0 and dp at 1. And the answer to this is that the value for dp at 0 is the cost at 0, right? So we take the costs at 0, that's the cost of choosing to be at the first step, and this is the costs of choosing to be at the second step. From here, it's the same process as what we had before, right? We're going to iterate from 2 to n. And in this case, we're going to say dp at I is going to be equal to the current value of the step that we're on plus the minimum of dp at I minus 1, dp at I minus 2. So what we're essentially saying here is that we're going to take the cost of the current step that we're on and we're going to add it to which one is smaller, the one that's 1 step away or the one that's 2 steps away, right? We're just going to keep adding the smallest possible cost to our current step cost, and that's going to give us the cost as we increment through, moving through each step. Then finally, at the end, we essentially need to determine which one is lower. Is it dp at n minus 1? Or is it dp at n minus 2? Whichever one is lower would be our optimal solution in this case. So you see that on each iteration, basically we're storing what is the smallest possible cost to reach a specific step. And then what happens is at the end, we'll have the least expensive cost to reach either the n minus 1 or n minus 2 step. From either of those 2 steps, we could reach the top, right? So that will tell us which one is the best one to go to, right? And you'll be able to see this in action if we do like a print of the example that I have here, right? I said that the answer to this should be 6 because we're going to step through to all of the 1s and avoid all of the 100s. And you'll be able to see that exactly, right? There you go. The answer is 6. I encourage you to try this with a few different inputs and just sort of see that this does actually work. As we vary out the inputs, it will always find the optimal solution to step through this particular array. What is the cost of this particular function? Well, like the other one, it's O(n). It's linear time complexity. If we didn't have this ability, we wouldn't be able to solve this problem for large arrays. However, because we can use this idea of bottom-up dynamic programming, we can actually solve this problem now. We get our linear time complexity, which is really fantastic. So this is just another really basic example of how we can use dynamic programming. Now that you've got a few simple examples under your belts, we're going to take a look at some more complex examples to better understand, some more interesting ways that we can use dynamic programming. So thanks so much for watching this video. I'll see you in the next one.